In this question, we again want to calculate probabilities, or we're dealing with probabilities, dealing with a normally distributed population. But if we glance ahead to part A, what's different is that we're given the resulting probability. What's missing is the statement that the value that we're comparing x to. So in this problem, we're told that in a city of 937,758 people, the number of people who purchase a new phone within a month of its release are normally distributed with a mean of 84,940.4079 and a standard deviation of 2,954.0029. These people are referred to as early adopters. We want to find the value that corresponds to the 65th percentile of early adopters. First, we'll open up Desmos and set up the normal distribution, just like we have before, where our mean is 84,940.4079, and our standard deviation is 2954.0029. From there, we can turn on that visualization for the normal distribution, open up the cumulative probability tool, and click that zoom fit button to get a good view of our distribution. And now what we want to do is determine what this missing value would be, so that if x is less than or equal to that, the resulting probability is 0.65, meaning that data value represents the 65th quantile, or 65th percentile, 0.65 quantile, or 65th percentile. To do that, we'll set up a left statement because we want x to be less than or equal to some value, but we want to change the compute method from area to bounds. Now what's happening is Desmos is calculating the value we're comparing x to generate a specific probability. And we want this to be 0.65, I believe, let me double check. Yep. So if we have the 0.65 quantile, that's the same thing as the 65th percentile. We're given this value, which in this case is written as times 10 to the fourth. So it's written in scientific notation. If we output that value, we'll just get the number itself written in standard form. So we get 86,078. 0.6457. That's the number that represents the 65th percentile of early adopters. Then in part B, we're asked how many people would need to purchase an upcoming phone within the first month of release to be in the 65th percentile of early adoption releases for this city. So if 86,079 people, we need to round that to the nearest whole number since we're talking about people, buy a new phone within 1 month, then this launch would be in approximately the 65th percentile of early adoption releases. In the next problem, we have a similar setup. We're going to be looking to find the values that we're comparing x to, but we also aren't given explicitly the probabilities over on the right. So in this case, in a particular county, birth weights for full-time babies are generally modeled using a normal distribution with a mean of 6.9 and a standard deviation of 1.2 pounds. So we can refresh to clear out all that information, set our mean to 6.9, our standard deviation to 1.2, and turn on the visualization for our normal distribution. In part A, we want to find the value that corresponds to the third quartile of birth weights. This is going to require us to know that the first quartile is equal to the 25th percentile, second quartile is the 50th percentile, and the third quartile is the 75th percentile, or 0.75 quantile. So we want to know what value would be the 75th percentile. We'll change this to, again, compute bounds and a left probability statement. and we get the value 7.7094. Then in part B, we want to find the value that corresponds to the first quartile. So that would be 0.25 quantile, or the 25th percentile. Now all we need to do is just change that value on the right-hand side of our probability statement, and we get 6.0906. Then in part C, we're asked to find the interquartile range for this distribution. That's just going to be a subtraction step. Since we have Q3 and Q1, the distance between those two values would be that result we want for part C.